In our last video, we started talking about equilibrium. We had said that many reactions proceed in both the forward and the reverse direction, and when the rates in those two directions are equal, the reaction is said to be at equilibrium. We had said that equilibrium reactions obey a law of mass action, also called an equilibrium constant expression. And we wrote that by taking our equilibrium constant, which is a capital K, and then setting it equal to either the concentrations or partial pressures of our products over the concentrations or partial pressures of our reactants raised to a power equal to the coefficient. If we use concentrations, we had put a C here. If we used partial pressures, we put a P here. I am going to just put an EQ just as a generic equilibrium constant because then it can either be partial pressures or concentrations. So we said this was equal to the concentration or partial pressure of products over reactants each raised to a power equal to its coefficient. We did say that we were going to exclude pure solids and liquids from our expression. Right? We're only going to include gases and solutions. And our equilibrium constant for a particular reaction is always going to be the same at the same temperature, right? At a given temperature, it doesn't matter what our initial concentrations are. Once it achieves equilibrium, that ratio of products to reactants will always be the same when we're at equilibrium, and that's important to note. We can use the size, so the actual numerical value of our equilibrium constant, to determine the extent of our reaction. So the equilibrium constant can be used to determine the extent of the reaction, and again, this is at a particular temperature. And by extent, do I mean, is it mostly products? Is it mostly reactants? Do I have an appreciable amount of both, right? Which is favored during at equilibrium? So kind of those three possible outcomes if our equilibrium constant is large. And we're going to define large as greater than 10 to the third. So one, if we have a large equilibrium constant, and again by large we're going to say greater than 10 to the third. If this is the case, and it's helpful to remember, right? I'm just going to write this over here on the side. My equilibrium constant, and I'm going to do it in terms of concentration, so we can put a C here. It's going to be products over reactants, right? Raised to powers equal to the coefficients, but it is products on top, reactants on the bottom, right? So reactants are going to products, and then vice versa. And when we're saying extent, we're saying, okay, is it mostly this? Is it mostly this, or do I have, both? Well, if I have a large value for my equilibrium constant, right, and we just think about this mathematically, that means that my number on top, right, is much larger than my number on the bottom to get a big answer. So if the number on top, right, is bigger, if I have a large equilibrium constant, it's mostly products. So when we have a large equilibrium constant, it is product favored. So the reaction goes mostly to completion. We're still considering the product side complete. And the equilibrium mixture, remember at equilibrium we have both reactants and products, but if the value from an equilibrium constant is big, the equilibrium mixture contains mostly products, right? The number on the top here is bigger than the number on the bottom, so I can get a large value. So the equilibrium mixture consists of mostly products. Kind of the other way to say that is we would say that it's a product favored reaction. And then if it's small, right, the opposite, right, if I have a small value for my equilibrium constant, and again, capital K, I'm putting an EQ, you could put a C, you could put a P, it doesn't matter. So don't be confused by the fact that I'm using a C here and an EQ here. Here I'm using a C because I'm writing brackets, so I'm writing concentration. Here I just want to be, open for everything. If I put a C there, I don't want you to think that it doesn't count if there's a P instead. That's making sense. I hope it is. So anyway, if I have a small value, right, that means that my number on the bottom is going to be larger, right? When we do this math, right, when we calculate this fraction, if I want a small value, then I'm going to have a bigger number on the bottom. We're going to define small as less than 10 to the negative third. So if my equilibrium constant has a value that's less than 10 to the negative third, we're going to consider it small. Our reaction is going to be mostly reactants, right? My number on the bottom needs to get bigger. So the reaction does not, I'm going to say, occur to a significant degree. And the equilibrium mixture contains mostly reactants. And we're not saying all reactants, right? We're saying mostly reactants. I do have some products, right? We forward some products, but it lies more towards reactants. The same with this one up above, right? It's not all products. It's not going to completion. If it did, I wouldn't draw an equilibrium arrow. I would just have an arrow going in one direction. So mostly products. There's still some reactants, but it's product favored. This one we would say is reactant favored. And then our third scenario, it's kind of in the middle. So number 3. We could say an intermediate value for our equilibrium constant. So it's between 10 to the negative third and 10 to the positive third. So somewhere in between there. And this time the equilibrium mixture will contain comparable amounts of both reactants and products. What did I say? Comparable, acomparable. and products. Comparable, appreciable, I use both of those. Basically, we have both. You have reactants and you have products, one not much more than the other. So a comparable amount of both. So if it's large, let's go back and look at this. If it's a big number, this number on top is much bigger than the number on the bottom, so mostly products. If it's small, right, this number on the bottom is larger, so mostly reactants. And then if it's in between there, right, these two numbers are closer to each other. One isn't much larger or much smaller than the other. So we have an appreciable amount of both. Well, examples. If I give us the following reaction and equilibrium constant, so let's do 2 nitrogen monoxide, which are gases, plus an oxygen gas, and it forms 2 nitrogen dioxide. And our equilibrium constant for this, and this is at 300 degrees Kelvin. Again, remember, equilibrium constants do vary with temperature, but at the same temperature, that ratio is always the same. So for this one, my equilibrium constant is 4.2 times 10 to the 13th. So that's a pretty big number, right? If I go look at what we're considering big, big is larger than 10 to the third. This is 10 to the 13th. So at equilibrium, this reaction is going to favor products. So product favored. Right, this is bigger than 10 to the third. Another example for us, I have iodine, and I know iodine at room temperature, right, is a solid, but we're doing this one at a much higher temperature, so it is a gas. That's a G. And this is at 800 degrees Kelvin, so really hot. And my equilibrium constant for this one is 4.6 times 10 to the negative 7th. So that's considered small, right? If we go back up, it's less than 10 to the negative third. So smaller than 10 to the negative third. So this one is reactant favored. Right, the other way to say this, because we said at the top, right, kind of our first sentence here, it's used to determine the extent of the reaction, right? This one almost goes to completion, right? It's product favored, so thinking that we're starting here and going here, right? Even though we can establish equilibrium with anything, this is the perspective we're looking at it from. It's mostly in this direction because we're favoring products. This one, because it's mostly reactants, a very small amount of this occurs, right? It's mostly this and very little bit of iodine by itself, right, instead of its diatomic form. So it's not, right? It's not occurring very well. So I would say that this reaction occurs to a large extent. This reaction occurs only to a small extent. We can also use the equilibrium constant to predict the direction of the reaction that it needs to proceed in to achieve equilibrium. And to do that, we're going to define another value called our reaction quotient. So reaction quotient. And the abbreviation for that is a capital Q, and then usually with a subscript C because we're going to be defining it in terms of concentrations. And we actually set this up very similarly to how we set up the equilibrium constant. It's just remember when we plug in concentrations and solve for Kc, those concentrations have to be equilibrium concentrations. When we set it up for QC, they can be any concentrations. They don't necessarily have to be at equilibrium. And in fact, that would be important. I'm going to go back up and add this here when we started, right? Equal to the concentration or partial pressure of products over reactants at equilibrium, right? They have to be equilibrium concentrations. They have to be equilibrium partial pressures. If they're not equal to the equilibrium constant, right? Instead, they'd be equal to my reaction quotient. So let's add this here if you haven't already, right? The concentrations and partial pressures must be equilibrium concentrations or partial pressures, right? Remember, we can establish equilibrium starting with just reactants, starting with just products, starting with both reactants and products, and then as the reaction proceeds, eventually it achieves equilibrium. We need to use those equilibrium values to plug into our expression when solving for our constant. So they must be equilibrium concentrations or partial pressures. If we go back down to our reaction quotient, right, it's still going to be concentration of products over concentration of reactants raised to a power equal to the coefficient, but they do not need to be equilibrium concentrations. So the ratio is set up in the same way as equilibrium constants are, but the concentrations do not need to be equilibrium concentrations. And if you're doing it in terms of partial pressures, just substitute partial pressure for concentrations in the sentence. Equilibrium concentrations. So if we were to use our generic reaction, and this time I'm just going to use A and B instead of A plus B going to B plus C. Right? If we were to set this up for equilibrium, I would have the concentration of B on the top, and I would put an AQ here. B mole to B, guess that doesn't matter. Raise it to the B power, because that's my coefficient, over the concentration of reactants. Again, it has to be at equilibrium. Raise it to the A power, because I have A moles. If I set it up without equilibrium concentrations, so I'm leaving the EQ off of this, I end up with my reaction quotient. By then comparing the reaction quotient to the equilibrium constant, we can determine the direction that our reaction is going to proceed. Things want to reach equilibrium. So if it's not at equilibrium, it's going to shift in whatever direction it needs to achieve equilibrium. Equilibrium's our goal here. So we can compare QC to KC and determine the direction that the reaction needs to proceed in to achieve equilibrium. Right? It wants to achieve equilibrium. That's our goal. If it's not there, it's going to go in whatever direction it needs to go into to get equilibrium. So just we want to remember reactions move towards a state of equilibrium. Right? Once QC is equal to KC, right? We are at equilibrium when those values are equal, right? When they're the same, then I do have equilibrium constants plugged into that equation. So kind of our three scenarios, right? If Q or QC is greater than K or KC, they could be P's. So if Q is, sorry, I think I might have said bigger. If Q is smaller, right, I used the less than sign there. If Q is smaller, so I'm going to go back up and look at these again. Remember, it's products over reactants. And I'm saying that this one is too small, right? I need to make it bigger. So if this is too small, what that means is the number on the top is too little, or the number on the bottom is too big, right? Either way, that's going to give me a smaller answer. So if this is too little and this is too big, right? Which way do I have to go to make it equal to this? I'm going to have to go towards products, right? It's going to proceed in the forward direction. I need to make B bigger. I need to make A smaller. So I'm going to go towards B. So if Q is less than K, right, the ratio of products to reactants remember, it's products on top, reactants on the bottom, and that ratio is too small. So to reach equilibrium, we need more products. So to reach equilibrium, reactants must be converted to products. So the system proceeds in the forward direction. Again, forward assuming reactants are on the left and products are on the right. Right, towards products, P for products. If the opposite was true, right, if Q is bigger than K, right, again, remember K is our goal, so Q is too big. We need to make Q smaller. So if we go back and look at our reaction here, or our ratio, right, this time we're saying this is too large. So my number on the top is too big, my number on the bottom is too small, right? So to make this smaller, I need to decrease this, I need to increase this. So we're going to go towards A, right? We need less B, more A. Again, remember, K is our goal. It's too big right now. I need to make that ratio smaller. So the ratio of products to reactants is too large. To reach equilibrium, products must be converted to reactants. So the system proceeds in the reverse direction. So towards reactants. So if right? My reaction quotient is too little. We need more products, less reactants, and it's going to go in the forward direction. If my reaction quotient is too big, right, too large, we need to decrease the amount of products, so it's going to be favored in the reverse direction. Third scenario, they're actually equal to each other. If this is the case, we're already at equilibrium. Right? If they're equal to another, our concentrations that we're plugging into our reaction quotient ratio, right, into that expression are actually equilibrium concentrations. So the reaction is at equilibrium and there's no shift in direction. Remember, it is a dynamic state. We're not going to say it's not going to react. It's just that it's going to go towards products and reactants at the same rate. So no shift in direction. Remember, equilibrium is a dynamic state. The forward and reverse direction are still occurring. It's not like it stops. It's not like it doesn't do anything. It's just that the rates in both directions are equal. So no shift in direction. An example for us. So given this reaction, N2O4, producing 2 nitrogen dioxide, and we're given our equilibrium constant for this, and it's 4.65 times 10 to the negative third. Looking at the size of that equilibrium constant, what is favored at equilibrium, reactants, products, or both? Good. Hopefully you're looking at this and you're saying, okay, 10 to the negative third, it's a little bit bigger than 10 to the negative third, right? Because it's 4.6. So probably an appreciable amount of both. It is kind of small, so maybe a little bit more reactant than product. But again, remember looking at the size of this, right? Its actual magnitude, we can determine the extent of our reaction. That's not our actual example though. What we're going to do is we're going to determine in which direction does the reaction proceed when our concentration of N2O4 is 0.0456 molar, and our concentration of NO2 is 0.589 molar. So what we're going to do is we're going to solve for Q, and we're going to compare it to K, and we're going to determine which direction is it going to favor. Note in this sentence, it doesn't say the equilibrium concentrations are, or I don't have an EQ after, I don't have an EQ here, right? We don't know if they're equilibrium concentrations or not. So what we're going to solve is for our reaction quotient. We do need to set that up. Remember, we set it up in the same way that we set up our equilibrium constant expressions. It's just that they're not necessarily equilibrium concentrations. So concentration of product raised to a power equal to its coefficient over the concentration of reactants raised to a power equal to its coefficient. I'm then going to plug those values in. So 0.589, I am going to square it, right, because I'm raising it to the second power. And then 0.0456. Just like with equilibrium constants, we do not need to show our units on our reaction quotient. It does have units. In this case, it would be molar, right? Because I'd have molar squared on top and molar on the bottom, so it would work out to just be molar. So remember, they have units. We just don't need to show them. So I'm grabbing my calculator here. If you want to play along, it would be highly encouraged. If you need to hit pause, by all means do that. And I end up with 7.61. Again, I don't need to show units. It has them, but it's typical to not show them. So I'm going to then compare my value for QC to my value for KC, right? And 7.61 is much larger than 4.65 times 10 to the negative third, right? My value for Q is greater than my value for K. So what that means, right? My number on the top is too big. I have too much of this, too little of this. So it is actually going to go in the reverse direction. So it's going to proceed towards reactants. We could say in the reverse direction. So again, we're setting up our expression, right? Just like we did when we're setting it up for our equilibrium constant. It's just that the numbers that we're plugging in don't need to be the numbers at equilibrium. And then compare our two values, right? Compare my value for QC to my value for KC. Since it's too large, I have too much of this, not enough of this. So we need to remedy that by going towards reactants.